Differentiating under the integral sign is an operation in calculus used to evaluate certain integrals that would otherwise be impossible through interchanging the order of integration and differentiation. This method of differentiation under the integral sign, otherwise known as the Leibniz integral rule, concerns integrals depending on an extra parameter such as t, as noted by Conrad. Sachs specifies that on November 11, 1675, German mathematician and polymath Gottfried Wilhelm Leibniz demonstrated integral calculus for the first time to find the area under the graph of y equals f of x. Leibniz is famously known as one of the fathers of calculus, introducing us to infinitesimal calculus, which comprises of integral calculus and differential calculus. This is the branch of mathematics concerned with areas on the curves, minima, and maxima, just to name a few. Sachs also states that Leibniz adapted the integral symbol from the letter long S standing for summer. The long S is simply an archaic form of what we know as the lowercase letter s.
Hey there, today I'll be going over the proof of the Leibniz rule. Let's get into it. Our equation is fx equals the integral between bx and ax of fxt dt. We'll start by differentiating both sides. Then our left side becomes d over dx, the integral between bx and ax of fxt dt equals the right hand side, which changes to the integral between bx and ax of partial f over the partial x dt, plus the function in relation to our upper limit fxb db over dx minus the function of our lower limit fxa dA dx. Now we have made the Leibniz rule. On to the proof, we'll start by letting theta xab equal the integral between bx and ax of fxy dy. This is going to be equation 1 for later. Using fundamentals of calculus theorem, the integral of capital fxy dy equals lowercase fxy, and the partial of f over partial y equals capital fxy. This will be equation 2 for later. Using our equation 1 and 2, theta of f of x, a, and b equals the integral between bx and ax of the partial f over partial y dy. After cancelling out, we get theta fxb minus fxa. We'll start by dividing both sides by partial a, appearing like this. fxb will become 0, leaving us with negative partial fxa over partial a, which equals negative fxa. From equation 2, we stated partial f over partial y equals capital fxy. After subbing in, we get this equation, and from our previous proof, we showed partial theta over partial a is equal to negative fxa. Subbing in theta, we get the same equation as before, shown here. This is equation 3. For the derivative with respect to b, we'll have partial theta over partial b equals partial over partial b of fxb and minus 0 like last time. We ended up with the left side equaling partial f over partial b, which is capital fxb. This is equation 4. Because theta is in the function of 3 variables, we can come together using the chain rule. d theta over dx equals partial theta over partial x times partial x over partial x, plus partial theta over partial a times partial a over partial x, plus partial theta over partial b over partial x. After cancelling, this is our final result. Finally, subbing in the rest of the equation gets us d over dx, the integral between bx and ax, capital fxy dy, equals the integral between bx and ax of partial f over partial x dy, plus equation 3 times partial a over partial x, plus equation 4 times partial b over partial x. This is the Leibniz integral rule.
The Leibniz integral rule is useful for definitive integral questions that cannot be solved using other means, such as integration by parts or use substitution. As such, this rule can help solve questions that would otherwise be very difficult or impossible to solve. A simple example of applying the Leibniz integral rule is the following function. At first glance, it doesn't seem that integration by parts or use substitution will work here, so instead, we're trying to use a simplified Leibniz integral rule to solve it, as the upper and lower bounds of the integral are constants rather than functions of x. We'll first turn this specific integral into a family of integrals Gn, with n equals to 5 as a specific integral. We can then apply the Leibniz integral rule to it to find g-n and get a partial derivative of t to the power of n minus 1 over ln t, which should give us t to the power of n. And we can then integrate t to the power of n towards affected t, and find that we'll end up with g-n is equal to 1 over n plus 1. Now, performing an indefinite integral on g-n, we're able to find gn as ln n plus 1 plus a constant. By substituting n is equal to 0 into our original gn, we'll find that g at 0 is also equal to 0. And since ln at 1 is also equal to 0, c has to be equal to 0. And now that we have a solution for gn, we can substitute n is equal to 5 back into the original formula to find the answer to the original definite integral, which is just ln 6.
Hi, today we're going to use the Leibniz rule to find the derivative of an integral. Here we have an example of f of x equals to the integral of sine of x to cos x with respect to square root 1 plus t cubed to dt. To find the derivative of this function, we have to use the Leibniz rule's right hand side, because f prime of x is equivalent of this function is equivalent to the left hand side of this function. So to use the right hand side, we have to use the given information that we can see from the function. So partial f on partial x is equivalent to that we can get from this part of the function, which is very easy because there's no x. So we can just write it as 0. And f of xt, which is just the function itself, which is 1 plus t cubed, square root 1 plus t cubed. Alpha of x and beta of x is given from the function here. We can know that it is just sine of x and cos of x. So alpha x is just sine of x, and beta of x is just cos of x. And later on, we're going to need the derivative of alpha x and beta of x given from the right hand side of this formula. So the dA on dx is just cos x, and the dB on dx is just negative sine x. Now that we have written all the information that we need on the right hand side to use the formula, we can just write f prime of x equals to d on dx integral of cos x sine of x square root 1 plus t cubed dx. We're just writing out the left hand side, and now we can equate it to the right hand side, which is the integral of cos x sine x, plug in the df on dx that we had, which is 0, dt plus f of x beta. We can find f of x beta just by subbing in b of x into f of x t, which is just 1 plus cos cube of x, and dB on dx is just negative sine x, and to find f of x alpha, just write this out, 1 plus cos cube x, and to find f of x alpha, it is just square root of 1 plus sine cube x, where you just replace the alpha with the t. So to continue on to our function, it will just be minus square root 1 plus sine cube x, and the last part, which is dA on dx, d on dx, which we found before is cos x, so cos x. And now we simplify this part, which is just negative. We just get rid of this part because it's just 0. So it'll just be negative sine x square root 1 plus cos cube x and minus cos of x square root 1 plus sine cube t. And that's how you use the Leibniz rule to find the derivative of an integral.
Okay, you can unshare your screen if you don't mind. There you go. I had to do it. All right, thanks guys. Has anybody got any feedback they'd like to give this particular group? Any thoughts? Renee's rally? Any positive comments? Anybody would like to? I thought that was pretty good actually. I know it went a little bit long, but I thought they did very well. Any comments? Okay. All right, well done guys. Once you're done, you don't need to hang around, so thank you for that. I do appreciate it. And as I said, we'll make sure that gets sorted out by the end of StuVac. Okay, so that's Renee's rally, and I think we said fans, didn't we? Well, I'm not.
Just I think I fixed the video problem. Like, should I just